Hello, everyone. In our last discussion session, we tried to learn how to decompose a vector into its components. Uh, in this session, we are going to deal with static cases where this resultant of all the forces is equal to zero. We know that by this Newton's second law, the resultant of all the forces would equal to mass times acceleration. So if the system is in static case, then the acceleration should be zero. And this is what we are going to deal with in statics and mainly in the rest of this course. We have a weight force that is always vertically downward and is equal to mass times gravitational constant. Usually in your problems, you are given W, the gravitational force, and not the mass. So you do not need to multiply mass by gravitational constant, and you can directly use the weight force uh, in your equilibrium equations. Uh, well, for example, imagine you have a system like this. We have two cables that are connected to a point A, and it is carrying a weight, and it is in a static case, so the resultant of all the forces equal to zero. It means that TAC plus TAB plus 736 is equal to zero, the sum of these three vectors. What you can do in these problems, especially the problems that you have three forces, is that you can draw a triangle. On two sides, you have two of the forces, each two of the forces, and the other one on the other side, because the sum of TAC and TAB should be equal to the opposite of the weight force, because the resultant of these three forces is equal to zero. So if you show the resultant of TAC TAB by this red arrow that I have drawn, then it is exactly opposite to the weight force. So then the resultant of all the forces would equal to zero. In this case, you can directly calculate, without decomposing the vectors into its components, you can calculate the forces by the law of sines, which says each force or each vector dividing by sine of its opposite angle. For example, here TAB has an opposite angle of 60 degrees, and that is equal to another force over its sine of opposite angle, and that is equal to the third force over sine of its opposite angle. So with this relation, the last equation, 736 over sine of 80. So you can derive TAB and TAC directly. But it is not a recommended method, because maybe you need to learn how to decompose vectors into its component and then write the static equilibrium for each direction and derive the forces separately, actually in a set of equations. For example, you're going to do that in this example. We have two cables, AC and BC, and we have a horizontal force 660 Newton that is imposing on point C. So if you draw the free body diagram, you're going to have something like this, which AC force and CB force are along the direction of the cables. Then, there's a point here. Actually, when you don't know the magnitude of the force and the direction, well, you know that the direction is along the cable, but you don't know if it's in the CA direction or the AC direction. So this is the same for BC. It doesn't matter in free body diagram how you draw the forces. The arrow could be pointing towards C. But the thing is, you know from this problem that these are two cables, so they can only carry tension forces. So AC is carrying a tension force on both sides. But so if so the force that is imposing by cable AC on point C should point outward from point C, and the same is true for BC. So in this case, when you solve the set of equations, if you derive a magnitude with minus, for example, minus 60, then you know that there is something wrong with your calculations, because it could not have a magnitude of minus 60, because then you should change the arrow of the force, and then the cable would be in compression, which is not physically correct. So this is a good way to check. When you have cables, uh, try to show the forces in tension case, and at the end you can check if you get a positive magnitude, then your calculations were right. So here we know from the main static equilibrium equation that sigma f is equal to 0, and this is for the vectors. Well, when sigma f is equal to 0, then each component of this sum should equal to 0. It means that in x direction and in y direction, the sum of the forces should equal to 0. So let's start with the y direction. Well, we know from our last session that the component of FAC in the y direction is equal to FAC sine of alpha, and for FBC is FBC sine of beta. So this is actually this equation, sigma f of y is equal to 0. These are the only two forces that we have in the y direction. So then you can derive sine of alpha and sine of beta by the geometry that is given in the problem. You have the opposite side magnitude and the adjacent side magnitude, so you can easily calculate sine of alpha and sine of beta, and derive at the end the equation which is a relationship between FAC and FBC. Well, you have two forces, you have two unknowns, and you have two equations, so you must be able to solve this problem by writing these two equations. So let's go on with the sum of the forces in the x direction. And then in the x direction, you're going to have 660 minus FAC cosine of alpha, which is this component in the x direction, and FBC cosine of beta. So then you will have two equations, 1 and 2, for FAC and FBC, and you can then derive FAC and FBC separately. Okay, I think there's no other point here. All right. Well, this is a very nice problem. We have a color A that is moving along this horizontal rod, and we have a cable that is connected to it, and on the other side connected to a weight of 50 pounds. As I told you, actually, this 50 pounds is the weight force. It is not the mass. So you don't need to multiply it by g in order to get the gravitational force. You can directly use this value. And so what you have here uh, is you have a tension in a cable, and you're imposing a force P to hold this cable, or it's better to say hold this weight. And well, it is a static case, and you don't have any friction on this rod. The only horizontal force that is acting on color A is the force that you're imposing, which is P. And so let's draw the free body diagram. In free body diagram, if you consider the point that connects color and the tension, and in the cable, you have an upward force from the cable. You have P in the horizontal direction, and also you must have some force in the y direction, which is actually acting upon color A by this rod. And this is necessary to have this component in the vertical direction, because you have a vertical force, uh, actually vertical force component in the tension in the cable. So you need to, if you want to make it static, you need to have some forces in the y direction. Anyway, in this problem, uh, it was not required to calculate the vertical force. You just need to calculate P, and that is going to be easy, because if you draw the free body diagram, you have P in x direction and in y direction, and you have the cable force that has both x and y components. So in order to get P, you just need to write the equation in the x direction, which is sigma f of x is equal to 0, because this n force does not have any component in the x direction. So what you will do is that you write the x component of the cable force, which is 50 sine of alpha. This is the angle alpha, and when you multiply sine of alpha by 50, you're going to get the component in the x direction, which is actually the opposite side length of this triangle here. So this is the equation for sigma f of x, and you put them equal together. Well, if you want to write it in a more you have 50 sine of alpha minus P, because it is in the minus x direction, and you will get this. And you can calculate sine of alpha with the geometry given in this question. And then you will calculate P. So if you want to derive N force, then you need to write the equation in the Y direction. So in the Y direction, you're going to have 50 cosine of alpha equal to N. And that is how you can get the vertical force acting upon color A. Well, the difference between this question and the previous one is that in this one, you need to write both equilibrium equations, sigma f of x equal to 0 and sigma f of y equal to 0, to derive these two forces, because they both have horizontal and vertical components. But in this equation, your unknown force P only has horizontal component, and you can derive it just by writing sigma f of x equal to 0. Okay. Well, let's go and have a brief review in the 3D case. Well, imagine you have a force in 3D case that is that starts from point M and ends at point N, and we want to show how we represent this vector. Well, you know that the joining vector between M and N is equal to dxi, dyj, dzk, in which dx is x2 minus x1, dy is y2 minus y1, and dz is z2 minus z1. This is the vector that connects M to N. So when you have a force, then you have a magnitude of that force, and you have a unit vector. In order to represent this force in vector form, you have a magnitude and you have a unit vector. And the unit vector is equivalent to the vector joining M and N, but you need to normalize it to get a unit vector. So you have to divide it by d, which is the length of the vector joining M and N. So d is actually can be driven by the Pythagorean rule, which is square root of x2 minus x1 squared plus y2 minus y1 squared and z2 minus z1 squared. And when you get the unit vector lambda, then you can calculate the components of this vector in each of the directions. If you multiply lambda by f, then you're going to have f dx over d in the x direction, and the prefactor for I vector, and fy f dy over d, and fz f dz over d. All right. Well, here you can, if you draw a set of Cartesian coordinates, you can calculate the angle between the resultant force or any force with each of the coordinates, each of the axes. So, for example, cosine of theta would equal to r of x over r. And you can see it in this figure that if you multiply r by cosine of theta z, then you're going to get the component in the z direction. And you can do the same for the y direction and the x direction. So this is where these equations come from. And you also have the magnitude that it is again can be driven by the Pythagorean rule. So, well, in this question, we have two forces that are represented by their magnitude, P 450 Newton and Q 600 Newton. And you have the direction that is represented by angles. Well, for P, you have the angle between P and the y direction, and you have the angle between the projection of vector P over xz plane and the z direction. So here we need to calculate the components of P and Q by using the angles that we have. So, well, imagine you have x, y, z coordinate and you have a vector P that has angle alpha between with y axis, and the projection of P in the on the xz plane has an angle beta with the z direction, which is equivalent to what we have in this question for vector P. So let's name the projection of P on the xz plane pxz. Then if the angle, this angle between P and y axis is alpha, then pxc would be P times sine of alpha, which is actually the length of the opposite side of angle alpha in this triangle. So then you have pxz, then you can have the components in the z direction and in the x direction by multiplying this vector by cosine of beta and sine of beta. So px would be equal to pxc sine of beta, which is the opposite side, and pxc equal to cosine of beta, which is the adjacent side. So you would have pz, and if you substitute the amount of pxz in these two equations, you can get px and pz. This is what is done for solving this problem. You have P, and you have the magnitude of the P vector, and this is the term in the bracket is the unit vector for force P. And as I told you, you can derive px by multiplying P by sine of alpha and sine of beta. So you have here sine of 40, which is alpha here, and sine of 25, which is beta here. For the y direction, it is easier. For the y direction, you have py, p cosine of 40, which is the adjacent side. And you have for the z direction, pz equal to p sine of alpha cosine of beta. And well, for q, you have different angles. You do not have the angle between q and y direction, and you cannot directly use the equations for px and pz that they be derived for vector p. So here you have 55-degree angle between q and the xz plane. So, but it is quite the same, because if you want to derive the y component of q, you have to multiply q by sine of 55, which you can see here, which is the opposite side of this triangle. And for well, if you multiply q by cosine of 55, you will get the projection of this vector on the xz plane. And if you multiply this projection by sine of 30, you will get the component in the z direction. And if you multiply it by cosine of 30, you will get the component in the x direction. So this is what we have done here. 600 is the magnitude of q. Cosine of 55, if you multiply this by cosine of 55, you will get the projection on the xz plane. And if you multiply that by cosine of 30, you will get the x component. And like before, you can multiply q by sine of 55 to get the y component. And for the z component, first you need to multiply it by cosine of 55 to get the projection, and then sine of 30 to get the z component. You should pay attention to the minus and plus signs here, and this is the you can know the sign of the force in each component by just looking how the vector is oriented in this space. Well, q is obviously have a positive x component, positive y component, but negative z component, so you have a negative here. And p has positive sign in all three components. So in order to get the resultant, you have to sum the components in each direction. In the x direction, you need to sum the first terms, and for the y direction the second, and for the z direction the third. And you will get the resultant vector. And you can calculate the length of the vector by this equation, which is actually square root of x squared plus y squared plus z squared. Well, if you want to know the angle that this resultant force makes with each axis, then we had these equations: rx over r, cosine of theta y, ry over r, and cosine of theta z, rz over r. So if you take the arc cosine of these values, then you will get the angle for the resultant force with each of the axes. Well, in this question, we have the horizontal circular plate weighing 60 pounds that is suspended as shown from 3 wires that are attached to a support at D and form 30 angles with the vertical. Determine the tension in each wire. So so it's a bit actually laborious to draw the free body diagram for a 3D case, but it is always good to make a sketch and actually make a very approximate diagram. So, well, you know that you can translate the vectors in space. So let's say this is point O, which is the origin, which is the center of center of the plate, you have a force BD, which is in tension. You have AD, and you have CD. And you also have a weight force that is vertically downward, which is 60 pounds. Okay, so uh, here we have the three-body diagram. So we need to decompose each of these forces in X, Y, and Z components and write the equilibrium equations, which are sigma f of x equal to 0, sigma f of y equal to 0, and sigma f of z equal to 0. So what we have in this problem, where you have to set a suitable coordinate system. We have a coordinate system here, but in this problem, you take the y direction vertically downward, and then you would have x direction, and you would have z direction. Right, and okay, I can erase this one. All right. Okay. This is actually the coordinate system x, y, and z. So let's first write the equilibrium equation in the x direction. Well, let me show the positive signs here. This is the positive sign in x. This is the positive sign in y, and this is z. All right, and you know that they make angle 30, each of the forces, the y component. So if you multiply t of AD by sine of theta, you will get the projection of this force on the xc plane, which is this opposite side of angle 30. And if you multiply it by sine of 50, then you are going to get this vector, this projection on the x. Okay, and well, we know that AD should be in tension. So we have a force like this, and well, the x component obviously has a negative sign, so we have a negative sign here. And you can do the same for BD, but this time this has positive sign. So TBD sine of theta would get the projection, and multiplying by cosine of 40 would lead to the x component. And you have TCD, which also has positive x component, and multiply it by sine of 30 to get the projection, and then multiply it by cosine of 60 to, well, you can see in this triangle that this would be the x component. So this is what we write in the x direction. We have 3 unknowns and 3 equations. So we need to write the other 2 equations as well. In the y direction, all of the forces have minus sign. So you can easily get that by multiplying each force by cosine of 30, which is the projection on the y axis. So all of them has minus sign, except the weight force that is oriented downwards, so it has positive direction. And you can also write for the z direction the same thing, except that you need to have, when you get the projection on the xz, this is the projection vector, projection magnitude, you have to multiply it by cosine of 50 to get actually the adjacent side, to get the z component. And for BD, you have this angle, and in the z direction, you have to get cosine to get the z component. This is the opposite side. And this is the adjacent side. So this is the component in the z direction, and you have to multiply by sine to get the opposite side. And we have the same for TCD. You have 3 equations and 3 unknowns, and you can derive all the 3 forces based on these.